Welcome to Qualmark's Ask the Experts presentation today. I am Gail Eckert, Director of Marketing for Qualmark, and I'll be the webinar moderator. I am pleased that Qualmark supports these free events that keep our accelerated reliability community up to date about the latest HALT HASS applications and best practices. Today, the COE team presents HASS Proof of Screen, and we hope you will participate in the instant polls during the presentation, which are designed to share insights for you into peer practices. At this time, I would like to introduce today's presenter, Neil Dortenbaugh, the Center's Senior Applications Engineer. Welcome, Neil.
Thank you, Gail, and thank you all for logging in today, and I hope you find this presentation to be valuable. Here's an overview of what we're planning on covering today. I'll do just a very brief discussion of what HASS is and the purpose then of the HASS proof of screen. We'll talk about the two-portion proof of screen, the fact that we have an effectiveness portion and a safety portion, how to do it with limited samples if you have expensive samples or just a few to work with, and what to do when you've got products that you would expect to fail in the effectiveness screen but don't, that they're actually valuable. And we'll talk about key performance indicators as well. And then I want to get into proof of screen in terms of fatigue in the SN curve, an analysis of just an overview of a paper that's available where we do a mathematical analysis that says proof of screen works. And we'll have time for questions afterwards. Please feel free to submit those via the chat line. And would actually like to take the opportunity now to do our first poll, because I'm curious to find out how many folks that are tuned in now are currently doing HASS in some form or plan to start HASS in the very near future. So if you should be seeing popping up on your screen an opportunity to click and select your current level of HASS performance at your company. We have, I think, about 45 seconds to get clicked in here, and then we'll show you all the results of the poll. But this will help me understand really how many folks are actively doing HASS, how many of them are planning to start HASS soon, would like to get it started. So if we'll give you a few more minutes here, it looks like we're racking up the responses from what I can see. And we'll see. Everybody should get a little bit of insight from these. I tried to pick questions that would not only give you folks some insight, but give me some insight. I've got a few in here that might prove me wrong when I look at the results, so I'm looking forward to getting to those. And I guess you're all seeing our nice graph now. So we've got 40% of the respondents performing HASS now, so that's good, with 34% not doing any HASS. Several there with plans to get started soon. So that's good, because I'll be asking some questions of the folks who are performing HASS now, and we've got a good audience to respond to those. So let's move on, and I'll step through the concept of HASS in general, the overview. Essentially, HASS is your opportunity to find and correct defects that are creeping in through design and process changes. And it makes production happen faster. It'll reduce cost. You'll get higher out-of-box quality. That's always nice. And higher field reliability, reduced cost, all the good things that come with shipping a mature product that has had variabilities, had those outliers eliminated. And as you can see by the graph, the whole idea is push the product out, find the ones that are going to fail, and catch them before they get out the door. Now, HASS is very different from burn-in, and it is not uncommon to have HASS replace burn-in in a manufacturing facility. The whole purpose of burn-in is to weed out infant mortality. Ideally, you're taking the first piece out of the bathtub curve. The effectiveness of it for doing that's been brought into question over the last several years because we've pretty much figured out how to build ICs, and that was one of the key purposes of burn-in, although it's still effective for high-power devices, and also verifying function at elevated temperature. Now, really, the purpose of HASS is to verify continuously that the limits you found in HALT haven't changed. You don't have any new weak links that have crept into the process. So HALT, or the HASS, is based on your HALT results, and you're pushing it as far as you can to check and see if you can catch the edge of any distributions of new failure modes that are coming into your product, or something that some of your upstream suppliers may have done to you. In the process of HASS development, as a general overview, the first line is critical. You've got to do HALT before you do HASS. I'm assuming everybody online is familiar with the concept of HALT, basically finding out what the true operation and destruct limits are of your product and pushing them out as far as you can, regardless of the intended environment, regardless of the specifications. And that failure analysis and corrective action has been done on those, verification HALT done to determine those actual limits. In HASS, it's critical that you're doing functional tests continuously, so the functional test development needs to be done. We've talked about the fixture design and validation because that's an interesting challenge as well when you implement HASS. The last two items in red are what I'll be stepping through today. Developing that HASS thermal and vibration profile, and then going through the process of proof of screen. So those final steps in getting a screen developed and implemented. Now, let's start out with a graph that many of you are familiar with, I suspect, where we talk about the idea of the stresses that are being applied to the product in this process. A typical environmental stress screen will stress the product within specifications or at specifications. But when you go into HALT, you'll go into this margin discovery and expansion process where you will find the true operating limits and the true destruct limits of the product. Now, you just got a couple of data points here. You're testing 4 to 6 units when you get into HALT. So you have identified these operating limits. Clearly here we're talking about a thermal stress because we have both upper and lower limits shown here. And we'll have the operating limit, which is a point of soft failure. If you take the stress away, the failure mode goes away. And then we also have destruct limit, where we actually cause a hard failure. So you identify those points in HALT. Now, in reality, there is some distribution around those failure modes. And once you have completed your corrective actions, those distributions should be due to just 1 or 2 failure modes that are associated with the absolute technological limit of your product. These are just things you can't do anything about. You understand them. This is where your product is. But there is a distribution to those failure modes. The goal in HASS is to set up a screen that will push the product far enough that if anything has shifted and the details of those distributions have moved in, they will be identified in HASS. And a typical or a classic HASS consists of a precipitation screen that you see here and then a detection screen that you see here. The purpose of the precipitation screen, which is done with the product typically unpowered and with functional tests not running, because we're outside of the operating limits. we don't expect the product to actually be working, but we're inside the tails on this destruct limit. So we don't expect to be causing hard failures due to these known defect modes. If something has caused this distribution to creep in, a one-of defect because of a soldering error or something that's happened in the process, this precipitation screen will force something to fail so that you will be able to see it later when you get to the detection screen. The detection screen, the second stage, is done with the product on, powered, functional, doing all the functional testing. You are detecting anything you broke in the precipitation screen and also detecting any changes in this operating limit. If something has caused this distribution to creep in, then you will have a failure during this detection screen. All of these limits for precipitation and detection screens are based on what we learned in HALT. They're not based at all on the product specs, and that's a key and important part of the HASS screen development. Now, one thing to consider when you finally finish doing HALT, it's not unusual for the operating and the destruct limits to be so close together that separate precipitation and detection screens don't make sense. There's just not really enough room here to do this. And so what you'll wind up doing is just a detection screen based on the operating limits that you find in HALT. So this shows that basically zoomed in on that center section. Our screen limits based on this distribution around this lower and upper operating limits. And this gives me an opportunity to ask the question. I've often said that most of the time people wind up moving to a single stage screen like this rather than doing the classic screen. So what I'd like to find out is, of those 40% that are listening or that are currently performing HASS, if you could click and describe your process for me. Are you doing a single pass screen where you're doing detection only, running the product continuously, or are you doing precipitation and detection screens where you'll start off running outside of your operational limits, product not being tested, and then drop back down to a detection screen where you turn on the product and do your functional testing. So we'll give you all about 30 seconds to click there and let us know, and we'll show you all the results of that as well. I have found that there are situations where products have very clear operating limits that are simply due to temperature limits on a component where a microprocessor just shuts down. It's not going to work. But you don't hit any destruct points until far after that. So a two-stage screen makes a whole lot of sense. But if you have a product where about the time everything quits working, it also starts breaking, then a single-stage screen makes sense. Well, as you're seeing the results now, that's not too far off from what I suspected. We've got about a third of the folks that are doing precipitation and detection screens separately, the rest doing just a detection screen within operational limits. And there's always going to be others. There's lots of varieties and customizations that are done for HALT and HASS. So that's a good piece of information for me and you both. If a detection screen alone is what makes sense, then by all means, go with it. Now, there are a few critical unknowns when you start setting up that screen. If you notice, I talk about the HASS screen limits, but we don't really know what this distribution looks like, and we don't have any idea what these tails look like. We only tested a few units to find this operating limit point. What are we going to do about the fact that we don't really know exactly where to put this so that we don't fail products that are good, but we do fail products if they're causing this tail to creep in. This is what proof of screen is for. So we've got some basic guidelines that we've developed as a starting point when you're setting up a HASS screen. And these are based on historical information and math and what's been shown to work in the past. And what we've found is we take what we have found for a destruct limit for vibration in HALT and reduce that by 50%. And typically we'll begin by running a vibration duty cycle of 50% of the screen. So half of the screen the vibration is running, and that vibration is running at 50% of the destruct limit. The thermal range that we go over is 80% of the operating range that was found in HALT. So it's guard banded, but not by a whole lot. And then we'll build a screen that is 5 thermal cycles with 50% vibration running during those 5 thermal cycles. I like to set up 5 cycles primarily because it gives you the opportunity to tune your screen in production later. You really get a solid idea of how effective the screen is by watching when failures drop out after you've run a few thousand units through your screen. If everything's dropping out in the first 2 passes, then you know you can start backing that screen off and save some time and money. With 5 cycles, you have some resolution there on on where things are really failing. And if you go to proof of screen and find out that that might be too stressful, you reduce the stresses rather than reducing the number of cycles so that you can keep that resolution in your results. And proof of screen is the process that we use to empirically demonstrate that those levels will result in an effective and safe test. 2 portions, effectiveness and safety. Now you'll notice that the HASS vibration level is backed off a significant amount, whereas the thermal range is not really backed off that much. The vibration portion is truly accumulating fatigue on the product. So by backing that off to half, we're dramatically reducing the fatigue that we accumulate in the product that might contribute to a shortening of life. We're not really producing thermal fatigue in a HASS screen. There's not enough time, and that's not our goal. Our goal is to identify failure modes that are sensitive to thermal extremes or sensitive to thermal ramps, not necessarily fatigue in thermal. So we know we're not going to really hurt anything by pushing to 80% of the operating range that we found in HALT. So let's talk about that empirical demonstration of proof of screen. We've got how to set up the starting point. Now we need to do, first I need to learn how to work my buttons here. Okay. We've got the 2-part screen. We're demonstrating that the screen is effective. I like to do that first to see that the screen will indeed force marginal products to fail, and that we will induce some performance degradation in these marginal products. We'll talk about performance degradation and key performance indicators as well. So if the screen is effective, it will do these things for us. We also need to prove that it is safe. It is the vibration that we use is an aggressive vibration. It's possible to wear things out with it if you try hard enough. We proved that in HALT. So we want to show that the fatigue that we induce during the screen will not remove an unacceptable percentage of product life. The definition of an unacceptable percentage is usually 10%. Seen mil-spec saying 5% is okay in a screen. We want to be sure that is not exceeded even if the product is screened more than once, because you find a failure, you fix it, you want to run it through the screen again. So proving that the screen is effective is a process of showing that we're not taking too much life out of the product, even when we have to run that product through the screen multiple times. Keep in mind the importance of functional testing. functional testing while the product is under stress is critical for both HALT and HASS. You can't ever relax and say, I'm just going to put it in, stress it, take it out, and see if it still works. What you're going to miss are the transient failures, the things that only happen under stress but don't happen otherwise. That's what turns into intermittent failures in the field, NDFs when they come in through service, and they're the really expensive ones that you want to get rid of. And remember that a key part of functional testing is power cycling. And power cycling should be done both during the hot and the cold portions of the screen. At cold, power cycling is more fatiguing because your product is nice and cold before you turn it on to get it hot. You leave it off long enough to cool down, which is a minute or two. In hot, you're more likely to see errors due to timing, startup timing issues, because when all that electronics gets hot, it's more sensitive to timing issues. So you're really looking for two different classes of failures when you power cycle cold versus power cycling hot. It's very important. And proof of screen also gives you a chance to really understand if your functional test is working well. You're going to be running it over and over. You're going to be seeing if failures are indeed identified and you're getting enough information from the functional test to go back for failure analysis. So you need to know all you can when you get to that stage. So let's make sure that that functional testing is being done during all portions of the proof of screen. Now the first part of that screen, as I said, is effectiveness. Let's prove that it will find marginal products. Well, here's challenge number one. In order to do that, you have to have marginal products. Products that you would expect to fail in the screen, but that pass the production line tests. This can be a little tricky. One of the things you can do is take product that is down rev, that is stuff that you used in HALT, does not have some of the corrective actions that you put in as a result of HALT. Still passes the testing, but you expect it to fall out in HASS. Those are good to use if you've got some down rev products. If you've been doing trials or you've had this unit out in the field doing some work on it and people have failures that have been returned as no defect found, those are wonderful to use in your proof of screen. They can be very valuable, whether they fail or not, they're valuable. So if you have any of those that you can get in for your proof of screen, you can get them. Another option is seeded failures. That can be tricky. It's really hard to do a bad solder joint on purpose that's so bad that it'll come apart come apart in HASS and be something that would have affected product life. You certainly can look at component values that you may be able to substitute in that the unit will function at room temperature. Capacitor values you can cut in half or double part of the time and not really see anything during normal operation, but you would expect HASS to catch that. You can also try changing the torque on some of your fasteners to make sure that the vibration will loosen up those fasteners and show them to you in HASS and let you know that your torques might not be being done correctly in production. So there's some ideas at least for seeded failures, and it may take some imagination on your part for creating product that you expect to see fail in the screen. But again, it's important that it passes the functional testing that would normally happen in production. Now, ideally, you want these products to fail in one pass through the screen. And by a pass, I mean if we've decided that 5 cycles is what we're going to do, then it should fail during those 5 cycles in the screen. If you find that you're not precipitating failures, you might want to look at changing the screen, changing your fixturing perhaps, or changing your product configuration. One of the problems and places where you have to do some intelligent decision making that will come up is that in HALT we'll often do the testing with the cover off the product and maybe other modifications for airflow, etc. But in HASS, you're testing a full up product, so you have a different product configuration. Maybe you think about doing HASS before you put the top cover on, and put the top cover on at the last. So those are things to consider. If you need to reduce the stress of the screen, most likely you're going to need to be changing vibration, because that's the stress that really does the fatiguing. So look at maybe changing level or duty cycle on the vibration, or dwell time thermally. Now, if you've got no defect found products from the field and they don't fail in the effectiveness screen, but you do have other indicators that the screen is effective, perhaps some of those failed and some of them didn't, look at those NDF products, do some deeper analysis to see if you can find a failure in them, but don't make any changes to them that might affect the failure mode, because you can use these later in the proof of screen. So that's essentially the effectiveness portion, and it's fairly straightforward from an empirical standpoint. Find things you expect to see fail and see if they fail. Safety is also fairly straightforward. Here we want to demonstrate the screen will not take an unacceptable percentage of life out of the product. So, easy enough. We take known good products and run them through the screen 20 to 50 times. And one of the things I don't really get into here, I believe, is how many units to use for this safety portion of the proof of screen. I usually think in terms of a chamber full, or at least 10, ideally up to 20 being used for safety, and running it through the screen 20 to 50 times. If you find, or at the end of 30 passes, that the screen has not caused end-of-life fatigue, wear-out type of failures, then you have some confidence that 2 passes through the screen, that's kind of a worst-case assumption, where it fails, gets run through again, you will remove less than 2/30 or 6% of the useful life of the product, and that's quite tolerable. So if you run 10 products through the screen, nothing has failed by the end of 30 passes, you can feel pretty good about the idea that you've got a screen that's not taking a lot of life out of the product. If you're seeing failures before 20 cycles are complete, then you need to do some closer looking. Maybe we need to reduce the intensity of the screen, because, and an important point here is end-of-life failures. Failure analysis on everything is very important. Through HALT, we say that over and over again, and here we say it over and over again. You cannot simply say, well, it was outside of spec, so that's probably what killed it. We need to understand what failed, and especially understand if it's an end-of-life type failure. Now, this whole concept here, the idea that if 2 passes do not make a unit fail, or I'm sorry, if 30 passes do not make a unit fail, then 2 passes will remove less than 2/30 of the life. That is the subject of the end of the webinar here, and the topic of the paper that I've written that goes through an analysis to show that that logic is valid, even though the stresses that are being used are nothing like the stresses being used in real life. So, now that I've described that, I have another question for you folks, and that is, if indeed you're currently using HASS, how many passes did you use when you performed your proof of screen? If you did a safety portion, did you go, in the old days, being probably 6 to 10 years ago, we used to say 10 passes through the screen is fine. And if you don't see any failures, sort of make that worst case assumption that more than the next pass it would have failed, then 1 time through takes less than 1/10, I can tolerate that. Since then, I've heard reports of people running good product for 100 times or more and not seeing failures. Typically what you find is if you've got a new failure, it fails very quickly in HASS, or new failure mode. It'll show up very quickly. So if you have good product, it will tolerate many, many passes through this screen. So I'm curious to see, and it looks like we've got about enough responses now. Let's look at the graph here. And that's not too far off from what I'd expect to see. I see a third of the folks not going through the pain and agony of the safety proof of screen. And that can be a result of the fact that it takes units and time to do it, and a confidence level that I know the level of vibration I'm putting into this product, I know how my product is designed, I'm confident enough that I'm not going to take the time and use the products to do a proof of screen. It's an engineering judgment call, and depending on your situation, it may make sense. And it looks like the majority are doing more than 20, which is good, and a reasonable fraction doing less than 10, which was probably folks who started their screen years ago when that was reasonable. So that's 10 or less in that category. Okay, that's some interesting information for you. I would expect nowadays I say 20 is a minimum, and you change that number perhaps based on other factors that we'll go into next. So, as I said, all known good products should pass the safety portion of the proof of screen. And then they should be able to pass a full qualification test, where more than just the functional test that you do at the end of the production line. Now, you really have to do that failure analysis. I always joke that the important stuff I say 3 times, so failure analysis, I think this is the 3rd time for it. See if it's a wear-out type of failure. If it is, then let's reduce the screen strength. Now, is the failure, quote, legitimate? This is a bad product. It had a true infant mortality or a design issue that should have been spotted. Well, if that happened, let's look at the screen and functional test and see if we need to increase the functional test, the screen strength rather, or if we need to make some changes to our functional test so that we can catch that in a single pass rather than after multiple passes through the screen. Now, a question that we run into a lot of times. Look, I've got a $10,000 unit here. You want me to use 10 of them in proof of screen. You're out of your mind. What can I do with just 1 or 2? Well, you know what? We can do that, but it's very simple. When you reduce your sample size, you've reduced your confidence. The way to increase the confidence is to increase the number of passes you do through the screen. Really, as I said before, if you've got a good product, you've gotten rid of all your failure modes, and you've effectively ruggedized it, it can be expected to tolerate 50 to 100 passes through the screen without end-of-life failures. So what I'm saying is at least 50 passes on a single unit without failure would give you the confidence level you need. Ideally, if you have the time, you just keep going until you see a fatigue failure. And then you have a really good idea of what that one unit did. And if it's sufficiently far out, then you can move into the screen with confidence. Another thing you can think about is implementing what we call key performance indicators, where you're looking not necessarily for a failure, but for a degradation in performance, a reversible degradation in performance. So that can be valuable to look at, and I'm going to be discussing that shortly here. Now let's think about what I've been talking about. If you've got NDF products or marginal products that don't fail, what can I do with those when I run them through the effectiveness portion of the proof of screen and they haven't failed. Well, those are perfect for putting into the safety portion. What you do is you run those through, and if they don't fail at all in the safety portion, now you can say, oh good, those were indeed good products, they shouldn't have failed, and I have some confidence in that. If they fail at pass 13, then you've got something to worry about. Because if you're using through NDFs that have come back from field use, I've heard most reliability engineers saying that about 50% of returned products really are functional. They're fine. Probably a defect in what I refer to as the AMOC. That's the Autonomous Mobile Organic Key Presser, otherwise known as operator error. And it reduces the number of new samples that you need to use for the safety portion. You've got these units that came back from NDF, so you're not grabbing brand new samples for the safety portion now. You save a little money there. So now that I have popped up that 50% number, I'm curious. What have you seen just in general when you see units come back from the field as failed? How many of those in your testing are found to be defect-free? Just as you can see, I'm looking at vague numbers here, but more than half, about half, less than a quarter. This is be a good piece of information, I think, for all of us. One of the key pieces that HASS can do for you, if those units that are being returned as NDF really do have a transient failure mode, HASS catches those. So if you're seeing a lot of NDFs, it can indicate there really is something wrong. It's just something that you're not able to duplicate when you get the unit in. So any of you who have some insight into what you see coming in the back door through failures that have happened in the field, warranty issues, what fraction of those are we seeing functional when tested? Let's give a few minutes here so that everybody gets a chance to click some buttons, and as soon as you see those responses stabilize, Gail, we'll move on up and show the results. I've always been interested to see this. Well, that's a pretty wide distribution, more than half for a quarter of them and less than a quarter for about a quarter of you. So, and about half, so half or more, half of you agree that's correct, less than half of you agree that's correct. Sounds like it's spread out a bit. See now, if I wanted to be bold and bragging, I'd say, you see, those folks that are seeing less than 50% of the ones that are doing HASS. I should have tried to figure out a way to work that into the poll. Anyway, thank you very much for that information. That's interesting. Let's talk now about the key performance indicators that I've mentioned, how you can get new value out of HASS and learn more about your product by monitoring key performance indicators. Now, the key performance indicators are those functions on the product that give you a warning that a failure is impending. Before it truly fails, becomes detectable, there may be parameters or characteristics of the product's performance that indicate an impending problem. And what you have to do is sit down with design engineers who understand the product well and say, what might be, things like noise floor levels or timing tolerances, or what things you might use as prognostic indicators during a product's life that tells you that the product is nearing its end of life. Are there indicators we can monitor and look at them as part of a functional test, and also as part of the failure mode and effect analysis? You might come out of that with some ideas for key performance indicators. What can I monitor that will tell me that the product might be starting to fail? You can verify whether or not these are good key performance indicators by figuring those out before you start HALT. and monitoring them in HALT to see if they are indeed indicators of impending failure. So, and not simply the way the product behaves when you hit it with extreme temperatures. So look and see what happens during HALT. See if the number of units that might exhibit a failure, or rather, you can say that you basically widen the distribution of what you're defining as a failure by looking at failure precursors. It gives you a broader range of units to look at and catch failures before they can get into the field. If you have a change that doesn't quite force a product to fail in HASS, but does cause some of these key performance indicators to peak, now you've got a new way to see it. And also, if you see shifts in these key performance indicators across the whole population, now you have an alarm bell to go off that says somewhere one of my vendors shifted a process. Did the KPI shift enough to make you want to say that unit's bad? Well, then now you're hitting engineering judgment calls. But it certainly gives you a new indicator that something's going on different. And by monitoring those points, you can learn a lot. So you carry over to HASS what you learned from HALT. It provides a mechanism for inducing a, quote, failure without actually forcing a product to become non-functional. Now, if I've got 3 or 4 units that cost $10,000 a piece, I can put all of them in my safety portion of proof of screen and just watch for KPIs. If I see a key performance indicator starting to creep up, I can pull that out of the live test, do some evaluations on it, understand what happened, but I'm not actually pushing it far enough to make it non-functional and non-shippable. So it can reduce the cost of that safety evaluation when you're doing expensive products, and it makes it more effective. So considering that concept of KPIs, that's one that I think I haven't heard mentioned much, that I talk about a lot. I know we use prognostics in product life to watch a product to see if it might be failing in use. But just out of curiosity, how many are using these KPIs as an indication in any type of production testing? Not just in HASS, but in anything you're doing as part of functional test. Are you looking at some performance indicator, not necessarily a hard failure, but an indicator that something's starting to flake out as part of burn-in or run-in or any other testing that you're doing as part of your production line testing? It seems to me that it's not used extensively and could be used more. Pretty valuable. Oh, and that's not too far off from what I was thinking. The 43% that are currently using key performance indicators, that's a little higher than I suspected, but we still have the majority that aren't using those. If it's at all possible in your product to do that, it's a good trick to pull. And here's an example of a use of a key performance indicator. We were doing tests for a customer on a product, and the functional test protocol stated that if one of the failure modes was if it could not process input-output requests. However, we were able to monitor during HALT the inputs and outputs per second that it was processing and see if there was a degradation in it. Due to the nature of the test, there was always some variability in the number of IOs per second that it was being processed. But as we increased temperature and decreased temperature, we could watch and see if the IOs per second changed. And during HALT, we saw during hot thermal step that performance degradation, the units that showed the most performance degradation earliest were also the same units that failed first at high temperature, and it was due to a design defect. Now, as an aside, we also saw IOs per second drop going cold, but we didn't see any units with uniquely different rates of degradation. And so what we saw, things like this, here we have, I picked graphs from 3 different products, and here we have the temperature as we increase the temperature during HALT, and here are IOs per second. And I've highlighted on this product and on this product the places where they were really outside of the norm for IOs per second. They still hadn't failed, they were still processing them, but they were outside of the norm. But these 2 units were defective units, and they did fail early. The 3rd unit that you see here, it saw degradation as well. We expected that, but it did not show degradation that was extreme or out of line from the norm. So this is the kind of thing you can look for, and by pushing up part of the way up, you can find out what you've got for, what you, if your HASS screen is stopping here, you're going to go ahead and catch these units without forcing them to fail. Now I'd like to take a brief overview of the whole idea of proof of screen in terms of the SN curve. Let's taking a look at it using classical fatigue analysis. And we use the Wohler's equation. Oh, that's supposed to be up as an exponent. The fatigue is exponentially related to time and the stress cycles. So we have stress raised to the minus beta here, and this is the number of cycles it takes to cause a failure, is Wohler's equation. So the number of cycles that it takes to cause a product to fail increases logarithmically as the stress level is decreased, resulting in the very familiar SN curve, where this blue line represents how many cycles it took for a unit to fail. Here we have stresses and number of cycles indicated here. Now, if I take that and say, what can I do to show that HASS works using SN curves and Wohler's equation? I make some reasonable assumptions, and I say, I do have a couple of data points. I have a data point from my HALT upper limit for vibration. I have a data point from my HASS proof of screen, where if I've done proof of screen run my proof of screen 20 times and nothing fails, I assume it would have failed on the 21st cycle, use that as a failure point, and this is being done at a different level. With that information and some assumptions for beta, I can draw an SN curve. Now, granted, it's going to be an approximation, but the key here is we're not looking for absolute accuracy, we're simply looking for relative accuracy. So we can calculate the ratio between the stress with and the stress without the HASS screen. So here we have our HALT upper limit defining an SN curve, and here we have the level of vibration that we would pick in HASS, that half of that. And we'd only run it for 2 hours. A typical HASS screen is 4 hours. The vibe will, here I've assumed, be half that time, so there's 2 hours of HASS vibe. So this is where that spot would appear on that SN diagram. During proof of screen, I run 20 cycles. So here is my point of fatigue after 20 cycles through my proof of screen. I'm still below the line that I drew based on my HALT upper limit. So this is saying, if I run my 20 cycles of proof of screen, or even more, this starts to level out here, I should not see end-of-life failures here. Now, if a product has a failure, it's going to, if you think of it in terms of defects in materials, if you have even just a hole, which is the least stressful, if you will, defect that you can have, you will see an increase in beta of 2 to 4 times. If you have a crack, it will increase beta 10 to 100 times on a material. So the SN curve will be much lower for a material that has a defect in it. And you can see here, if I assume a beta of just 9 and I'm running it through HASS, I should see a failure immediately, because with that material constant, we should see that happening at 22 Gs. So my stress level of 25, perfectly safe if everything is normal, but as soon as something happens to shift that material constant, then I get failures right away. Now the question is, what happens? Let's do some mathematical analysis and see what the effect of HASS really is on product life. Let's calculate the time life in the field with HASS versus the time without HASS. And we'll see what fraction of product life gets taken out. And Mill Handbook 344A talks about the same type of thing. And when we run all those numbers through, sure enough, we see that the ratio of time with HASS in place versus the time to fail without any stressing at all is 0.95. So with a host of worst-case assumptions, we come to the conclusion that less than 5% of the total life of the product is consumed by going through it one time, if you know that 20 times doesn't cause a failure. And you will be effectively weeding out products that would fail early in the field. Now, I did do, as I say, a paper on that, and if you are interested in seeing that white paper, please feel free to indicate in the survey at the end of this presentation that you would like to get a copy of that, and we'll be happy to email that out to you in the next week. And it goes into the details of the math and the details of the assumption, and those can be interesting to dig into. And just to let you know, all of this process of the development of the screen and proving that the screen is safe and proving that the screen is effective are all pieces of the services that Qualmark's Center of Excellence offers. We have the expertise in-house that other people don't have, that allow us to help you integrate HALT and HASS into your facility quickly, effectively, provide you with education and training as necessary. And we do have a proof of concept program where you can come to us saying, prove to me that this works, and then we'll talk. And we will work up a design of experiment to demonstrate the effectiveness of HALT for your device, what things we can find, and then move from there into HASS. So we have those features available for you. And I don't know how we're doing for questions. Gail, have we got several questions that have come in? Anything that I can answer?
Yes, we do, and we have quite a few of them, Neil. I don't think we'll be able to get to all of them. One question is that we have 5 thermal chambers that we're running for HASS, but they don't include vibration. How good or bad is our HASS program?
We have found in HALT that vibration or combined environment is responsible for about half of the failure modes that we identify. That thermal hot and cold and rapid thermal responsible for about the other half. So if those relationships hold true, I'd say you're missing about half of them. I really hate to have the first vibration test be the truck on the way to the customer. And that's the reality of the situation if you're not able to do vibration on everything. So that's a key point. Consider, actually, take a look at our website. We've got some little bitty thermal or vibration-only tables that you can add to your existing thermal systems that might help you out.
Okay. Question is the HASS screen ever modified or updated? Why and how?
Yes, it's not unusual at all. One of the key things that can make it happen is a change in a vendor where, if you imagine a power supply subassembly that you now get from another vendor, and they've got the thermal limit on that supply set 15 degrees cooler than the thermal limits on your other supply. You understand why, it's acceptable, it doesn't affect your product life, you can very intelligently decide to back off the hot limit on your screen. So changes in the actual screen itself, yes, it makes sense. The other thing that can happen is as your product matures and you look at the risks, you say, I'm not going to do 100% anymore. I'm going to drop back to an audit. My levels have gone up. I don't want to buy another chamber, so I'm going to reduce the number of units that I'm testing once I understand my risk.
Okay, thank you. Another question is, what is the difference if the profile starts at cold temperature rather than starting at hot? What's the difference? What's the ramifications?
Yeah, really, the only one is doesn't have too much to do with HALT or with HASS directly, but the fact that when you close the chamber doors, the chamber is full of room air with its associated humidity. If you start with a cold cycle, you have a reasonable chance of condensing that humidity out on the walls and on your product and getting frost. If you start with a hot cycle and then go down to a cold cycle, by the time the chamber or anything in it gets cold enough to cause condensation or frost, you will have purged all the room air out by the nitrogen that comes in. So you're better off starting hot and then dropping cold so that you get the moisture out of the chamber.
Okay, thank you, Neil. Also, we've got someone that's looking to increase production next year, and they are wondering if they buy a larger chamber, will the table change means that they have to do proof of screen again since the vibration will be different?
Very good question, and that's one we routinely deal with. The answer is most likely no, you will not have to change. One of the things that we have to do, you look at the product's response rather than looking at the table input, because the product response is what you care about, and the product and the fixture really have a huge and significant effect on what your product is seeing. So we will look at the product response. If it is different enough that we think it might cause a problem, then we'll perhaps look at modifying the fixture to make those responses similar rather than looking at doing a new screen and doing proof of screen on it. So it's not an unusual thing to have to do. You sort of have to do that when you go from HALT to HASS, because all the numbers you got in HALT were typically done on a different system than the system you wind up doing HASS in. Yes, we're set to deal with that. And it's particularly important with our new chamber, the Q Fusion. You know you're going to be dealing with a failure, with a different type of table. So we look at product response and make decisions from there.
And I encourage all of you to visit our website to learn more about the benefits of Qualmark technology and services and how we've organized the company so that customers can achieve maximum effectiveness from HALT and HASS. Again, thank you everyone for attending Qualmark's Ask the Experts presentation today.
Thank you.